All right, let's dive in. The world of chemistry is basically a giant stage, and all the reactions are run by this whole cast of tiny, super important characters. Today, we're getting to know the three main players: atoms, ions, and radicals. And honestly, getting a handle on them is the key to understanding what really makes chemistry, well, do stuff. So let's start at the very beginning.
It really all comes down to this one central question. What actually happens when an atom, this perfectly balanced little particle, gets completely knocked off kilter? The answer to that is what introduces us to all the other really interesting players in chemistry.
Okay, so our starting point, our ground zero, you could say, is the atom. In its most basic state, it's pretty much the definition of neutral. It's stable, it's perfectly balanced, but what does that balance really mean when you look under the hood?
It all boils down to this super simple but really powerful rule. The number of positive protons packed into the nucleus is perfectly canceled out by the number of negative electrons zipping around it. This perfect one-to-one balance means the atom has no overall electrical charge. None. It's totally neutral. This is our baseline.
But, chemistry is all about change. And the first way we can smash that perfect atomic balance is when we start messing with its electrons. When an atom either loses or gains an electron, it suddenly gets a charge, and a totally new kind of character steps onto the scene, the ion.
Right, so here's the key idea. An ion is just a particle that isn't neutral anymore. See, by either losing or gaining one or more of those negative little electrons, that perfect balance with the positive protons gets thrown way off, and what you're left with is a net electrical charge. And ions, they basically come in two flavors. If an atom loses an electron, well, now it has more positive protons than it has negative electrons, right? So it gets a positive charge. That's what we call a cation. And hey, here's an easy way to remember it. If you lose something negative, you feel more positive. On the flip side, if an atom gains an extra electron, it becomes negatively charged, and we call that an anion.
Okay, let's make this real with a classic example. You've got a neutral sodium atom, Na. It gives away one of its electrons. What's left behind is a sodium ion, which we write as Na+. Now think about it. It's still got 11 positive protons in its nucleus, right? But now it only has 10 negative electrons to balance them out. That leaves it with an overall +1 charge.
So this really breaks down the key differences for us. An atom is neutral, an ion has a charge. For an atom, protons equal electrons. For an ion, they absolutely do not. And here's the big one. Atoms can often just hang out on their own, but ions? No way. They're super reactive because they're desperate to find another particle to interact with to get stable again.
Okay, so here's where it gets even more interesting. It's not just single atoms that can get charged up like this. The very same rules, losing or gaining electrons, apply to whole molecules too, those groups of atoms that are all bonded together.
And we call this a molecular ion, basically a molecule that's now carrying a net charge. Now here's a quick heads up because the language can get a little confusing. Sometimes you'll hear these also called radicals, but for what we're doing today, we're going to use a way more specific definition for radical in just a minute. So for now, let's just lock in that idea. It's a molecule with a charge.
And just like with single atoms, you can have positive or cationic molecular ions and negative or anionic ones. Here's a fun fact though. It's usually easier for a molecule to lose an electron than it is to grab an extra one. So it turns out, you're going to run into these positive cationic ones way more often in chemistry.
All right, so everything we've talked about so far, all this instability, it's all been about having an electrical charge, right? An ion is unstable because it's positive or negative. But what if I told you there's a third player in this game? A particle that's totally neutral, but is still insanely reactive. I mean, how could that even work?
We'll say hello to the free radical. This thing is a whole different beast. Its reactivity doesn't come from having an overall charge at all. Nope. It comes from something much more specific, and in a way, even more desperate. A single, lonely, unpaired electron.
Okay, let's be super clear on this. A free radical has no net charge. The number of protons and electrons are still equal. The problem is that one of those electrons is all by itself in an orbital, and electrons hate being alone. It's a super unstable situation. And here's the dead giveaway. The way we show this is with a single dot right next to the symbol. If you see that dot, boom, you know you're dealing with a free radical.
It's this unpaired electron that makes free radicals so incredibly reactive. They often kick off these crazy chain reactions. So it all starts when a stable molecule gets zapped with enough energy to split apart, forming two radicals.
Now that radical, with its lonely electron, is so desperate that it'll rip an atom right off another molecule. But in doing so, it creates a new free radical. And that new one keeps the chain going, creating a product and another radical. It just keeps going and going, a full-blown chemical chain reaction.
All right, let's pull it all together and bring our three main actors back on stage. You've got the stable atom, you've got the charged ion, and you've got the neutral but wildly unstable free radical. Each one plays a totally distinct and vital role in the big drama that is a chemical reaction.
So here's the bottom line, the cheat sheet for these guys. Your atom, that's your neutral, stable starting point. The ion, it's all about having a charge, positive or negative. A molecular ion, just a bigger version, a whole molecule with a charge. And the free radical, our total wildcard, it's defined by that lonely, unpaired electron, even though it has zero net charge. Each one has a totally unique identity and its own reason for wanting to react. Which brings us to one last thing to think about. If these three are the main actors in pretty much every chemical reaction you're ever going to study, which one do you think is really the star of the show? The truth is, it always depends on the play. Thanks for tuning in.